Atomic models: solid particle model, 400 BC, plum pudding model, 1909, nuclear model, Rutherford, 1910, solar system model, Bohr, 1913, wave mechanical model, Schrödinger, 1927. While the fundamental particles of the atom, Table 1.1, were being discovered, other physicists were performing experiments that laid the foundation for a fundamental revolution in the way all matter is viewed. In the mid-1800s, physicists were interested in the interaction of light and matter. One of the interesting things they found was that each element, when heated or sparked with electricity, gives off characteristic colors. A spectroscope was used to show that these colors consist of discrete wavelengths of light, called line spectra, not the uniform rainbow observed when white light is separated by a prism. The line spectra of most elements and compounds are very complex. Hydrogen, however, has a seemingly simple series of lines. In 1885, Johann Balmer found an empirical mathematical relationship between the wavelengths of the lines he observed in the visible region of the spectrum. When similar series of lines were found in the infrared, called the Paschen series, and ultraviolet, called the Lyman series regions, Johannes Rydberg extended Balmer's equation so that all of the wavelengths could be predicted. In 1913, Niels Bohr completed his theory of how the hydrogen atom is constructed. He assumed that electrons move around the nucleus in circular orbits. Using a solar system model, he was able to duplicate the Rydberg equation from fundamental constants already known to physicists. Bohr's most important contribution was the concept that electrons exist in only certain allowed orbits. This, along with Max Planck's description in 1900 of light as packets, or quanta, of energy called photons, aided Bohr in developing the solar system model of the atom. Tip: quantum mechanics has replaced classical physics for describing events at the atomic level. In 1924, Louis de Broglie suggested that if light can be considered as particles, then small particles such as electrons may have the characteristics of waves. In 1927, Erwin Schrödinger applied the equations for waves to the electrons in an atom and began the wave mechanical theory of the atom. For hydrogen, the results are very similar to Bohr's model, except that the electron does not follow a precise orbit. The position of the electron in the wave mechanical model is described by a probability of where it will be located. Also in the 1920s, Werner Heisenberg developed the uncertainty principle, which bears his name. It states that the position and the momentum of any particle cannot both be known exactly at the same time. As one is known more precisely, the other becomes less certain. Atomic structure: light and the atom. An atom or molecule usually exists in the lowest possible energy state, which is called the ground state. An atom or molecule that has more energy than the ground state is said to be in an excited state. When an atom loses energy in going from an excited state to a ground state, light may be emitted. To understand this light, we need to review the basic equations for electromagnetic radiation. The electromagnetic spectrum. Visible light is only one small part of the electromagnetic spectrum. Figure 1.1 presents a representation of the electromagnetic spectrum and some of its common uses. For example, we can see that microwaves have wavelengths from 10 to the power of -1 to 10 to the power of -4 meters. Figure 1.1, pictorial representation of the electromagnetic spectrum emphasizing the narrow range of visible light. Wavelength, frequency, and energy of light. All electromagnetic radiation may be considered as waves that are defined by the wavelength, pronounced as lambda, and frequency, pronounced as nu. The wavelength, see figure 1.2, is the distance between two repeating points, either two minima or two maxima on a sine wave. The frequency is defined as the number of waves that pass a point in space each second. Figure 1.2, definition of wavelength. The wavelength and the frequency of light are inversely proportional to each other, as shown in the graph and the equation below. Frequency, speed of light, lambda l times nu n equals c. The speed of light is 3.0 times 10 to the power of 8 meters per second. pronounced as meters per second, or ms to the power of -1, a number worth remembering, although it is provided on the exam. Wavelength has units of meters, often with the appropriate metric prefix such as centimeters, micrometers, pronounced micrometers, or nanometers, pronounced nanometers. Frequency has units of reciprocal seconds, s to the power of -1, also called hertz. Speed of light in vacuum, 3.0 times 10 to the power of 8 meters per second, ms to the power of -1. Max Planck found that the energy of electromagnetic waves is proportional to the frequency and inversely proportional to the wavelength, as shown in the graphs below. The proportionality constant, h, is called Planck's constant. It has a value of 6.63 times 10 to the power of -34 joule-seconds, Js. Planck's constant need not be memorized. When required for a problem, it will be given. Equation. Planck's constant times frequency equals energy, which equals Planck's constant times the speed of light divided by wavelength, spoken as Planck's constant times frequency equals energy, which equals Planck's constant times the speed of light divided by wavelength. Energy, wavelength, and frequency are all related. If the speed of light and Planck's constant are known, only one of these three variables is needed to calculate the others. Example 1.1. In this exercise, and all others in this book, it is recommended that you cancel the units with a red pencil or pen to verify the calculations. Question. What are the frequency and the energy of blue light that has a wavelength of 400 nanometers? Planck's constant equals 6.63 times 10 to the power of -34 joule-seconds. Tip, meters per second, m/s, and ms to the power of -1 all represent the same units. Solution. Substitute the given values into the equation. Wavelength times frequency equals the speed of light. 400 nanometers times frequency equals 3.0 times 10 to the power of 8 meters per second. Step 1. Substitute 10 to the power of -9 for the prefix nano in the wavelength. 400 times 10 to the power of -9 meters times frequency equals 3.0 times 10 to the power of 8 meters per second. Step 2. Rearrange this equation to solve for the frequency by dividing both sides by 400 times 10 to the power of -9 meters. Frequency equals 3.0 times 10 to the power of 8 meters per second, divided by 400 times 10 to the power of -9 meters. Result. Frequency equals 7.5 times 10 to the power of 14 reciprocal seconds. The energy of this light may be calculated directly from the frequency or the wavelength by using equation 1.2. Step 1. Calculate the energy using the formula. Energy equals Planck's constant times frequency. Energy equals 6.63 times 10 to the power of -34 joule-seconds, multiplied by 7.5 times 10 to the power of 14 reciprocal seconds. Energy equals 49.725 times 10 to the power of -20 joules. Energy equals 5.0 times 10 to the power of -19 joules. Correctly rounded. Or you can use equation 1.2 as shown below. Energy equals Planck's constant times the speed of light divided by wavelength. Energy equals 6.63 times 10 to the power of -34 joule-seconds, multiplied by 3.0 times 10 to the power of 8 meters per second, divided by 400 times 10 to the power of -9 meters. Energy equals 5.0 times 10 to the power of -19 joules. Important note. It is essential to ensure that the units cancel correctly when solving these problems. The meter units cancel each other because one is in the numerator and the other is in the denominator. The seconds units cancel because seconds appear in the first term and reciprocal seconds appear in the second term. Example 1.2. What are the wavelength and energy of light that has a frequency of 1.50 times 10 to the power of 15 reciprocal seconds? Solution. The relationship between wavelength and frequency is wavelength times frequency equals the speed of light. Substitute the given values. Wavelength times 1.50 times 10 to the power of 15 reciprocal seconds equals 3.0 times 10 to the power of 8 meters per second. Step 1. Rearrange to solve for the wavelength. Wavelength equals 3.0 times 10 to the power of 8 meters per second divided by 1.50 times 10 to the power of 15 reciprocal seconds. Wavelength equals 2.0 times 10 to the power of negative 7 meters. Step 2. Convert to nanometers using the metric prefix, where 1 nanometer equals 10 to the power of negative 9 meters. Wavelength equals 2.0 times 10 to the power of 2 times 10 to the power of negative 9 meters. Wavelength equals 200 nanometers. Step 3. Calculate the energy using the formula energy equals Planck's constant times frequency. Energy equals 6.63 times 10 to the power of negative 34 joule seconds, multiplied by 1.50 times 10 to the power of 15 reciprocal seconds. Energy equals 9.94 times 10 to the power of negative 19 joules.